This is the first presentation about the best methods for reducing carboxylic acids to primary alcohols. One important strategy is the use of hydride donors, such as lithium aluminum hydride, and in this video I'll shortly comment on the reactivity of various potential hydride donors. In the remaining videos about the conversion of carboxylic acids into alcohols, I'll discuss catalytic hydrogenation, borane, lithium aluminum hydride, silanes, the in situ activation of carboxylic acids followed by reduction, and treatment with samarium iodide as potentially useful reduction strategies. The reduction of carboxylic acids is one of the most difficult reductions in organic synthesis. This is because hydride or single electron donors convert acids into carboxylate salts. Carboxylates are not only difficult to dissolve, but also poor electrophiles and do not usually react with hydride or single electron donors. Therefore, the transfer of hydride to a carboxylate group only proceeds well if electron density is removed from the carboxyl group by some kind of activation. Esters, anhydrides or acyl halides, for instance, are often easier to reduce than free carboxylic acids. Also boranes or lithium aluminum hydride form strong bonds to carboxylates and then transfer hydride to the carbonyl group intramolecularly. Even some catalysts used for the hydrogenation of carboxylic acids form a transient bond to the carboxylate and thereby facilitate the addition of hydrogen to the CO double bond. To estimate the suitability of potential hydride donors as reducing agents, I have calculated the differences between the bond dissociation enthalpies for element oxygen and element hydrogen bonds. These numbers are in the colored fields, green indicating a high exothermicity for the conversion of an element hydrogen bond into an element oxygen bond. This enthalpy should correlate with the exothermicity of the addition of hydride to a carbonyl group, as shown here, because in this reaction an element hydrogen bond is cleaved and an element oxygen bond is formed. The numbers in brackets are the electronegativity of the corresponding element. To the left of the red line, the elements are less electronegative than hydrogen, and hydrogen would carry a partial negative charge in element hydrogen bonds. On the right side of the red line, elements are more electronegative than hydrogen, and element hydrogen bonds would be acidic, that is, the compounds would tend to donate a proton, not hydride. Thus, compounds to the right of the red line will usually not act as hydride donors. What this comparison illustrates is that the addition of hydride of the second and third group to CO double bonds should be possible due to the correct polarization of the element hydrogen bond and highly exothermic. Because of the low electronegativity of alkali metals, alkali hydrides are mostly ionic, but the addition to CO double bonds would be less exothermic than that of second and third group hydrides, despite the higher partial negative charge of ionic hydride if compared to boron or aluminum-bound hydrogen. Reactivity, however, is not only a thermodynamic but also a kinetic property. But isn't it amazing that the hydrides of boron or aluminum are potent hydride donors for organic carbonyl groups, while lithium, sodium or calcium hydride do not reduce ketones at all? Well, this is not completely true. There are some few examples in the literature of carbonyl group reductions with alkali hydrides, but most required either oxophilic additives or forcing conditions, and may even have proceeded by single electron transfer. Two such examples are shown on this slide. The reduction of the norbornenone only proceeded in the presence of methyl iodide, and under similar conditions, cyclopentanone, for instance, only yielded 0.5% of methoxycyclopentane. Norbornenone undergoes enolization more slowly than other similar ketones and, because of the high ring strain in norbornenes, reacts more readily with nucleophiles. These were the main two reasons proposed by the authors for this unique reactivity of sodium hydride toward norbornenone. In the reduction of benzophenone with sodium hydride, the reaction mixture turned blue, what indicated the formation of the ketyl radical anion. Accordingly, this reaction was not only a nucleophilic addition of hydride to a ketone, but proceeded at least to some extent by stepwise single electron transfer, followed by protonation. A larger number of examples can be found, however, of reductions with a combination of an alkali hydride with some activating reagent. These include various Lewis acids, sodium iodide, and transition metal salts. It has also been reported that magnesium hydride is a powerful reducing agent for CO double bonds when prepared as a slurry in ethers. This is an example of such an activation of lithium hydride with chlorotrimethylsilane. Still, probably because of the low solubility of lithium hydride, the reaction required 50 hours to go to completion. It is surprising that no silyl-enol ether was formed in this instance, and that only 1.5 equivalents of lithium hydride were required. Direct reduction of chlorotrimethylsilane is a further potential side reaction, but wasn't an issue in this case. So why are alkyl hydrides and calcium hydride so poor hydride donors for carbonyl groups? It has been suggested that free hydride does not add well to carbonyl groups because of a poor overlap between the small 1s2 orbital of hydride and the much larger pi star orbital of the carbonyl group. I do not find this argument too persuasive, because CH bonds, for instance, are quite strong despite the orbital size mismatch, and lithium hydride readily reacts with aluminum chloride where the orbital size mismatch would be even larger. Both lithium hydride and sodium hydride also react readily with borane in ethers to yield lithium or sodium borohydride. The fact that alkali hydrides react in ether solvents with boranes and aluminum compounds, but not with aldehydes or ketones, may result from the fact that boron and aluminum derivatives are strong Lewis acids, much stronger than the carbonyl compounds, because the empty p orbital of boranes has a lower energy than the pi star orbital of carbonyl groups. The hydride affinity, that is the enthalpy of addition of hydride to a molecule, is also larger for boranes than for aldehydes. Proton transfer reactions from alcohols are exceedingly fast reactions, what may explain why lithium or sodium hydride readily react with alcohols but do not add hydride to ketones. There are a number of other ways to rationalize the inability of alkali hydrides to reduce ketones. Small ions with high charge density tend to react more slowly than larger ions because of their tight solvation shell, which must be broken up in order for the small ion to react. This has been observed not only for addition reactions, but also for nucleophilic substitutions or redox reactions of organic and inorganic compounds, both in protic and in aprotic solvents. Another example of a small anion with high charge density would be fluoride, which in most protic solvents only reacts as a base, but does not readily undergo SN2 reactions at carbon or add to electron-deficient olefins. Hydride is assumed to have a similar size as fluoride and should therefore also be tightly solvated by ethers or dipolar aprotic solvents, what would diminish its reactivity. One could also argue in terms of Pearson's hard and soft acids and bases concept. Because hydride is a soft base and carbonyl compounds are hard acids, no fast addition of hydride to ketones or aldehydes is to be expected. One further reason for the low reactivity toward ketones must be the low solubility of ionic hydrides, caused by their high lattice energies. There are in fact examples of soluble complexes containing calcium-hydrogen or magnesium-hydrogen bonds which readily reduce carbonyl groups or imines. Solubility alone, however, cannot be the only reason, because as shown above, ionic hydrides react in ethers with Lewis acids, such as borane, and also with alcohols. Finally, there may be an intrinsic high activation barrier for the addition of hydride to carbonyl compounds. Such barriers have been found for fluoride and alkoxides and could also exist for hydride. It may also be unfair to compare ionic hydrides with the superb reducing agents sodium borohydride and lithium aluminum hydride. The latter two compounds are not only more soluble in ethers, but react with carbonyl groups by simultaneously acting as Lewis acid and as hydride donor, similar to aluminum isopropoxide in the Meerwein-Ponndorf-Verley reduction. Such an ambident reactivity may not be possible on the surface of an undissolved ionic hydride, because in solids each metal cation is surrounded by several hydride ions and each hydride by several cations, making the undissolved ionic hydride inherently less reactive than a dissolved monomeric hydride. To conclude, ionic hydrides can usually not be used as reducing agents for organic carbonyl groups, unless some special additives are used. More reactive are the covalent hydrides of boron, aluminum and silicon, and their use for the reduction of carboxylic acids will be discussed in the next presentations.